Most of us imagine the very early Earth as a prolonged, violent chaos, a hostile sphere of molten rock persisting for hundreds of millions of years. The physical evidence left behind contradicts that timeline. In Western Australia, geologists have recovered tiny, incredibly resilient minerals called zircon crystals, dating back 4.4 billion years. These zircons act as microscopic time capsules. The trace elements and oxygen isotopes trapped inside their crystal structures prove they formed in the presence of liquid water, interacting with a solid crust. The massive magma ocean cooled and solidified within perhaps 5 million years, while volcanic outgassing built a thick, high-pressure atmosphere. Within a geological blink of an eye, the planet's basic physical machinery was online. The structural foundation and pooling liquid water were ready for biology almost instantly. Life took advantage of that rapid organization early on. By around 3.5 billion years ago, microbes like these cyanobacteria appeared in the shallow waters and began performing oxygen-producing photosynthesis. This timeline chart plots the origin of that oxygen-producing life against the chemical composition of the sky. Biology started pumping out oxygen 3.5 billion years ago, but that gas only actually accumulated in the atmosphere around 2.4 billion years ago. That leaves a massive 1 billion year void. Trillions of tons of biological waste product were produced, yet atmospheric oxygen remained at practically zero. Biology was trying to change the sky, but something was deleting its progress. The early Earth operated as a colossal, highly reducing chemical sponge. The surface environments were filled with elements and compounds that aggressively hunted and reacted with any free oxygen they encountered. The primary culprit was the deep ocean. The early seas contained absolutely no free oxygen, but they were heavily saturated with dissolved ferrous iron, reacting as an immediate, impassable trap. Cyanobacteria lived primarily in the sunlit surface waters. The moment their newly produced oxygen diffused downward into the deep water, it encountered that dissolved iron. The oxygen immediately oxidized the iron, turning it into insoluble rust, which then sank directly to the sea floor. We can see the chemical graveyard today. These layered red and gray rocks, known as banded iron formations, are vast sedimentary deposits made of that rust. For hundreds of millions of years, the ocean acted as a defense system. It relentlessly stripped oxygen out of the water before it could ever reach the air above. Even if oxygen somehow managed to escape the ocean's iron trap, it immediately hit a second wall in the sky. This cross-section diagram illustrates the faint young sun paradox. Because the early sun was 30% dimmer than it is today, the planet relied on a thick, dense band of methane gas to trap enough heat to keep the oceans from freezing. Methane reacts violently with free oxygen. When oxygen particles drifted up from the water, they were instantly destroyed, converting the methane into carbon dioxide and water and creating an impassable chemical ceiling. Life was stuck in a chemical stalemate. Biology could not overcome Earth's iron and methane sinks without help from the planet's deep interior. Establishing an oxygenated atmosphere required a physical evolution of the Earth itself. The core problem for the bacteria was their own life cycle. When photosynthesizing microbes die and decay at the surface, their decomposition consumes the oxygen they generated while alive. It creates a closed loop with zero net gain. This geological cross-section shows the breakthrough. As the planet's internal heat cooled slightly, maturing crustal plates established stable subduction zones. Dead organic carbon from the seafloor was trapped in sediments and dragged deep into the mantle. By physically burying that carbon deep underground, geology permanently crippled the planet's capacity to consume oxygen. It broke the loop, allowing the waste product of life to finally accumulate at the surface. The stalemate finally broke around 2.46 billion years ago. The rake of tectonic carbon burial overwhelmed the planet's remaining chemical sinks. The proof is written in sulfur isotopes. A chemical signature called SMIF permanently vanishes from the rock record at this time. This happens because oxygen levels reached a critical threshold, just enough to form an ozone layer, which blocked the specific ultraviolet light needed to create the SMIF signature. But that ozone shield triggered a climate catastrophe. The rising oxygen rapidly scrubbed away the atmospheric methane. Without its potent greenhouse insulation, global temperatures crashed, plunging the planet into the Huronian glaciation, an ice age that lasted hundreds of millions of years. Oxygen acted as a destructive agent, shattering a billion-year climate equilibrium and nearly freezing the planet solid. Below the ice, life faced an even more direct crisis. For the anaerobic microbes that had evolved in a reducing environment, free oxygen was a reactive, lethal poison. Mass die-offs swept through the early biosphere. The surviving organisms were forced into a radical evolutionary pivot. They developed metabolic defenses against the toxicity and eventually learned to use oxygen for aerobic respiration, extracting up to 20 times more energy from organic matter. This energetic upgrade provided the fuel required for complex cells and eventually animals to evolve. The complex, breathable blue marble we inhabit is a tectonic achievement. It exists because the physical planet matured enough to allow life to finally succeed.